First speaker will be Xiaoyu Xu from Peking University, talking about profinite rigidity and almost rigidity in three matter.
Thanks for the invitation, and thanks to the organizers for this. My topic today is about profinite rigidity in three-manifold groups. So the basic idea for considering three manifolds is that the Thurston's geometrization actually builds a connection between the group theoretical aspects of three manifolds with the geometrical or topological aspects of the three manifolds. So let me first list a number of very well-known facts for these connections. So firstly, three manifolds are largely determined by their fundamental groups. Like for closed, orientable, irreducible, three manifold. The isomorphism type of the fundamental group determines uniquely the homeomorphism type of M, except for very easy counterexamples. Except for length spaces. So this is a starting point of why we consider profinite rigidity in three manifolds, because we can switch the group theoretical problem into the geometric problems in this case. So to be more precise, let me tell you like two more generalizations of this well-known fact. So the first one is a generalization by, actually not a generalization, but a step towards this kind of theorem in the history. So the first statement is that for let's not only consider closed manifolds, but also for compact manifolds. Orientable, let's say a spherical. And boundary irreducible. If there is an isomorphism between their fundamental groups that respects the peripheral structure, then the group isomorphism is realized by an homeomorphism. So I think this is mostly due to Wolfhausen many years ago. Another statement in this direction is that if we are less constrained about the asphericity, the peripheral structures, or anything, any conditions, we just consider the abstract isomorphism type of the fundamental group, and there is in that case we don't have like homeomorphism theorem, but we still have a kind of finiteness theorem. Let's just say orientable. The fundamental group determines the homeomorphism type to finitely many possibilities. I think many people have contributed to this theorem. So the main literature written down are by Johansen and Swarb around 79 to 80s. Yes, so as I've mentioned, the Thurston's geometrization can give a unified proof of these kinds of theorems that relates the group theoretical aspects to the geometric aspects. So the main question today is if we reduce the group theoretical information to the profinite informations. So the question is, what if we replace the fundamental group with the profinite fundamental group? Are these kind of facts still true? So what people have tried to do is to follow the routine of geometrization. So I have to first mention the theorem by Wilton and Zalewski. A series of papers. So the profinite fundamental group actually reflects some information in the geometrization. On compact orientable three manifolds with empty or total boundary. The profinite fundamental group determines the geometrization of the M. What I mean is that the profinite fundamental group determines, firstly, whether M is geometric in the sense of Thurston. And secondly, if it is geometric, it determines the geometry type. And thirdly, if it is not geometric, it determines the sphere-torus decomposition. So this significant result just reduces the question of profinite rigidity in three manifolds into the geometric cases. So let me first tell you what we do know currently. So regarding to the geometric pieces, what we know is that let's say relative profinite rigidity. So for the solvable geometry, this is the most easiest to be considered except for finite groups and virtually abelian groups. So For solvable geometry, the profinite rigidity does not hold. There are examples given by Steve and Funa, which is mentioned by Liu yesterday. And there is another example where profinite rigidity relative version does not hold in the geometric case. It's the ample pairs. Which is the topic of Liu's talk yesterday. And for the rest of the ciphered fiber geometry, it's just closed. There is a relative version of profinite rigidity proven by Wilks. And for non-closed cipher fiber spaces, I mean those with total boundary, there is a group level. I mean, among the isomorphism types of the group, there is a group level profinite rigidity. But since for non-closed manifolds, there exist non-homeomorphic manifolds with the same fundamental group, so let's say on the homeomorphism level, I have to distinguish them between. So these cases are more easily determined since they are very clear classifications of these kind of manifolds. The remaining most difficult case is the hyperbolic geometry. And this is actually the hardest part of this problem, so it's generally an open question in this case. So although profinite rigidity or relative profinite rigidity may not hold for geometric manifolds, there is a weaker version called almost rigidity, or some people may call it finite genus property for these kind of groups. So let me just write down a definition. The group G is called profinitely almost rigid. Within a class C of finitely generated residually finite groups, if it has a finite profinitely isomorphic genus. So even though profinite rigidity in these cases may not hold, the almost profinite rigidity in those cases are known. For the solvable case, this is a more general theorem by Grunwald, Pico, and Siegel, who deals with solvable groups. And for these Hempel pair examples, it is shown that Hempel pairs are the only examples that can be non-rigid in this case, so this is also true. And finally, for the most mysterious hyperbolic case, this is the almost profinite rigidity is also true due to a significant theorem of Liu. So almost profinite rigidity is something that what we expect to hold in like arbitrary finitely generated three-manifold groups. So the remaining question is whether these kind of theorems, in particular those three statements, hold in the non-geometric case. So indeed, the answer for non-geometric manifolds, the finiteness theorem, I mean the third one, is still true for the profinite case. So let me first write down this theorem. Fundamental groups of compact orientable three manifolds with empty or total boundary are profinitely almost rigid. Among themselves. Actually, the total boundary can be read out from the Euler characteristic, so one can change this among themselves to among three-manifold groups. There's not an essential difference for this statement. Let me first give a remark that the almost profinite rigidity for graph manifolds is proven by Wilks. Where he also disproved the profinite rigidity for graph manifolds. So the remaining essential case for theorem A is actually for the mixed manifolds. But I'd like to mention that there is a kind of contrast between mixed manifolds and graph manifolds, where in the mixed manifold case, we do have some kind of profinite rigidity in the graph manifold parts. So let me mention the second theorem. If we have two mixed manifolds, and we have an isomorphism between the profinite fundamental groups, so firstly, if F respects the peripheral structure, which is the same assumption as the Witthausen's theorem on the left, then the graph manifold parts of M and N are homeomorphic. Let me just write down a definition for this. If M is a mixed manifold, the graph part of M is the disjoint union of maximal graph manifold components and the JSJ decomposition of that. So this result shows a kind of a contrast with the disproval of profinite rigidity in graph manifolds, and the reason is that we have some more properties derived from gluing hyperbolic pieces onto the ciphered parts. So this kind of reflects Woodhausen's theorem on the leftmost backboard, and in particular, if M and N are closed, then there is no peripheral structure, so we automatically have this one. On the other hand, there is a result in the negative direction. So, however, if we do not require this peripheral structure, then there exist examples where M and N have profinitely isomorphic fundamental groups, but the graph manifold parts are even not homotopically equivalent. So the peripheral structure for this theorem is important.
So in 2, do you also assume that that respects peripheral structure?
Right.
In 2.
Yeah. In 2, there is no peripheral structure because they're closed. So we define maps between closed manifolds always respect peripheral structure.
So in general, you know, you permute the boundary components, but you don't know if you. So in general, you might send boundary to something not.
Yeah, in general, you might send the boundary elements to something which is not a boundary element.
If the boundary is connected, you still might
Yeah, when we permute the boundary components, we say that it respects peripheral structure. We also say that it respects. But the examples where they do not respect is that it sends a boundary element to something which is not boundary.
That can happen with surfaces, right? So you can have a torus with a single boundary component and a 3-hole sphere.
Yeah.
They're homeomorphic. The fundamental group's just F2, and there's no peripheral structure preserved.
Mm-hmm.
The boundary is connected in that example.
Yeah. For these examples, they're including some more complicated constructions, like at least 2 cipher fiber pieces will provide such an example. Yeah. Since when there is only 1 cipher fiber piece, we have group level rigidity for non-closed cipher fiber spaces, so there won't be such an example. So at least 2 cipher fiber pieces are to be needed in number 3. Okay, so what is the key ingredients in the proof of these two theorems? Since we have the Wilton-Zaleski result there, we have the geometrization. So the most essential part is to determine how those JSJ pieces are to be glued up. So let me demonstrate a simplest example for the proof. So let us restrict ourselves to closed manifolds. M, which has two JSJ pieces, M1 and M2 glued along a torus boundary. Let's assume M1 is hyperbolic and M2 is cipher-fiber space. And if there is a manifold N with isomorphic profinite completions, then the Wilton-Zaleski result shows that N has the same JSJ decomposition. Where N1 is also hyperbolic and N2 is a cipher-fiber space. So the Wilton-Zaleski result actually gives let's just say this is an isomorphism F, actually gives a splitting of the isomorphism into an isomorphism between graphs of groups. So in this case, this is more or less easier. We can write down the isomorphism between them. So there is an isomorphism in this way. So we actually have a kind of commutative diagram that describes the gluings between them. Let's say this is a boundary map of F1 and this is a boundary map of F2. So in order to derive information about the gluing maps, it is important to check the properties of the boundary maps of F1 and the boundary maps of F2. In this case, it's just which can be described by 2x2 matrix in z-hat coefficients, actually. So
maybe this is what I was asking. So in the hyperbolic case, you preserve the boundary components, but in the sacred fiber,
yes.
maybe you don't have condition one. It's the only case where you
Yes, yes. The hyperbolic case, it automatically preserves the boundary components. I think it's a result of Wilton and Powell. Yeah. In the cipher-fiber case, because they're automorphism of free groups, which goes everywhere. So the first result is that for the, let's first consider the F1, which is the hyperbolic part. So for the hyperbolic parts, and F1 is the given isomorphism. So the first result is that the boundary map of F1 is regular, which means that it is the profinite completion of an isomorphism I. And the second observation is that there are only finitely many possibilities. For the boundary map, when M1 and N1 are fixed. So this is the observation in the hyperbolic part, and a direct observation is that if the boundary map of F1 is regular, then the boundary map of F2 is also regular. Because the gluing maps are just regular. So this is the kind of observation. Yeah. So how do we apply this result to the theorems A and B? So it remains to consider the cipher fiber pieces. So for the cipher fiber pieces, okay, let's just simplify this property as what we called peripheral regularity of F1. Okay. So for the ciphered part, let's say M2 and N2 graph manifolds with boundary. If the isomorphism respects the peripheral structure, so this is where the peripheral structure plays a role, which the peripheral structure always holds in the closed case. And F2 is peripheral regular at some boundary component. then we know that these graph manifolds are homeomorphic. And that the boundary map, boundary F2, can be induced by an ambient homeomorphism. So like summing up these two lemmas gives the proof for the simplest example here for like those isomorphisms that need not respect the peripheral structure. I mean, lemma 2 will not hold, but but in that case, there is only finitely many possibilities for it. If you are given M2, there are only finitely many possibilities for the manifold M2. And there are modulo those induced by homeomorphisms, there are at most finitely ambiguities for the boundary map. So in that more complicated cases, we, with more discussions, we can also prove the almost to rigidity result. I think the closed case is interesting enough. So the thing to notice is that even we know that the cusp hyperbolic pieces are known to be profinitely rigid, in very general case, we cannot say that the mixed manifolds is profinitely rigid among three manifolds because there could be some extra properties in the boundary maps here which we cannot prove that whether it can be induced by an ambient homeomorphism of the manifold or not. But for like very for some special examples, like if the profinite isomorphism between the cusp hyperbolic manifolds, there are no exotic possibilities, or to be more less constrained, the boundary maps can always be induced by an ambient homeomorphism of the manifold. Then we can derive some examples of mixed three manifolds whose fundamental group is rigid among three manifold groups. So let's just write down a corollary. If M is closed, mixed three manifold whose hyperbolic pieces are all figure 8 not complements. There could be some more examples, but figure 8 not complements is the easiest to explain here. Then pi 1 of M is profinitely rigid among all finitely generated three manifold groups. This is because the figure 8 knot has full symmetry. In the case of full symmetry, the boundary maps can always be induced by homeomorphisms. So one can actually change this into like Whitehead link complement or something. I mean the boundary maps have to like satisfy some homological conditions. When the full symmetry is to say that whenever such a map satisfies the homological condition, it can be it can be realized by an ambient homeomorphism of the manifold. So for the one cusp case, there are at most 4 like automorphisms that satisfy the homological condition. So if it has an order 4 symmetry on the boundary, it has full symmetry. So since you're group theorists, I've introduced the group theoretical aspects in the group, but to my preference, I'd be more likely to understand these kind of phenomena in a geometric point of view. So what is the geometrical interpretations of these 2 lemmas, lemma 1? Since time is limited, I'll only include the lemma 1, the geometric explanation of lemma 1. So So let's just call this lemma 1 prime. So the geometric interpretation of the peripheral regularity is that for any kind of curve on the boundary, the profinite isomorphism sends such a curve to the curve on the boundary of the corresponding cusp manifold. So this kind of phenomenon is illustrated by the technique of den fillings of hyperbolic manifolds. Cusp hyperbolic manifolds. And we have a profinite isomorphism. Then there is a boundary homeomorphism. Such that for any boundary slopes, so actually, lemma 1 also holds for multi-cusp manifolds, which I've not written down, but it's the same. So for these slopes, we allow empty slopes. We have a profinite isomorphism between the den fillings. These are the den fillings along the slopes. So geometric implication actually says that if you have a profinite isomorphism between cusp manifolds, then you have infinitely many profinite isomorphisms between closed manifolds. So this is actually a very strong constraint on the profinite isomorphism itself, which makes me convincing that cusp hyperbolic manifolds should be profinitely rigid among themselves. So what is the application of this geometric insight? So maybe I have erased the Wilton-Zaleski result. So this den filling result plus the Wilton-Zaleski result actually tells you what is the exceptional slopes on M and N, like when they're profinitely isomorphic, they should have the same exceptional slopes because the profinite completion detects the geometrization. So with this observation, we are actually able to prove some examples of cusp hyperbolic manifolds whose fundamental group is profinitely rigid among three manifold groups. Let me list some easiest examples. The fundamental group of the following manifolds are profinitely rigid among finitely generated three manifold groups. So the easiest example is the complement of the Whitehead link. And there is another link complement with the same hyperbolic volume, which is called the hyperbolic sister ring. And there are more, so I'll just write some infinite families of surgeries on the three chain. For example, you can do like m minus half or 1 over n surgery on a particular two-bridge link. Where n is an integer. So a rough idea is that for a link complements, S3 itself is a very special exceptional net filling which can be detected from this lemma. And then for link complements, there are very highly developed theories for exceptional surgeries on link complements that somehow tells you that link complements with same exceptional surgeries as these one can be should be belong to a very simple finite list of manifolds. Yeah, any questions?
You can get arbitrarily many components. Like the other profinitely rigid, well, relatively profinitely rigid, link complement with arbitrarily many link components.
I don't know. We haven't found examples with for those links with many complements. I think 2 or 3 complements is what I found. I think this method could apply to some more link complements that I haven't studied. Yeah. So, I mean, this method is particularly useful in the setting of link complements because, firstly, it distinguishes link complements from all three manifolds, and then we have very developed theories and link complements that helps us to distinguish. Yeah. So the idea for this is that though we do not have very good methods to distinguish between closed hyperbolic manifolds, we still have good methods to distinguish non-hyperbolic manifolds. And yeah, there could be Dan fillings that produce non-hyperbolic manifolds. There's what we are going to use. So I have 10 minutes left, and let me just briefly tell you the history about the most important concept, which is the peripheral regularity. Actually, all of these theorems, A, B, and C, come from the observation of peripheral regularity. The history towards peripheral regularity is actually very zigzag. It's very complicated. So the starting point of this phenomenon is somehow called homological regularity with a coefficient, which is discovered by E. Liu. Which says that given finite volume hyperbolic three manifolds, orientable maybe, with a profinite isomorphism, then the abelianization can be decomposed as lambda times, let's say, phi. What do I mean is that lambda is invertible in the profinite integers, and phi is an, okay, let's say phi is an isomorphism between the homologies. So this result is actually highly based on three-manifold topology. It is kind of coming from the estimation of Thurston norms, which Leo mentioned yesterday. So this is a very three-manifold topology result. And the second step is to achieve a kind of intermediate result to the peripheral regularity, which is a peripheral regularity with the coefficient. With this coefficient, which is to say that the boundary map decomposes as the same lambda times let's say small phi, where phi is an isomorphism. So this is an intermediate step towards peripheral regularity. And I have to mention that, in fact, the weaker version, the peripheral regularity with coefficient suffices to imply this lemma 1 prime, the geometric version of that. So the reason for this one is we use the techniques of virtual retractions. So virtual retraction actually implies that these manifolds have a finite cover where all the boundary components are H1 injective, I mean injective on a homology level, so that we can deduce the peripheral regularity with coefficient from the homological regularity with coefficient. Yeah. And this is an ideal virtual retraction. And
so you want to allow many cusps, right? So
yeah.
So the units the lambdas could be different on different cusps?
No, they should be unified.
They should be the same.
Yeah. Or actually, they must be the same due to homological reasons. Because like you can, there is some slopes on the boundary which adds together to be null homologous, and they should have the same coefficient. If they have different coefficient, they will apply in bigger z-hat modules, which will not be null homologous. So actually, in this case, this lambda is the same as the lambda in the homological version. Yeah. So they should be the same, or maybe up to a plus or minus sign. So the third part is to improve the weaker version to the final version, which is peripheral regularity. So the main point here is to get rid of the unit lambda. So for this part, the main technique used is the relative profinite homology. So actually one can define a profinite mapping degree of this F similar to the manifold version. And there are two ways to compute this mapping degree. First way is to compute it on the boundary, which turns out to be plus or minus lambda square. And the second way is to compute it through the method of dense fillings I introduced before. And then, for some homological reasons, the dense filling is closed through a manifold, so we will get a cube here. And so, for this dimension shifter reason, it finally implies that there is no lambda or up to plus or minus signs. Okay, so actually, what we get is peripheral regularity plus homological regularity. Which is a very essential topic in profinite isomorphism between three manifolds. I think firstly introduced by Friedel and Boileau. So I have to say that this result is dependent on the relative profinite homology. So it depends on the boundary structure, and we currently cannot prove this plus or minus 1 result for a closed hyperbolic manifold. It's only for the cusp case. So I have -7 seconds left, and I will stop here. Thank you.